this book. Get through FRCR Part 1. This is the exam to obtain the title of Fellow of the Royal College of Radiology, or Radiologists, and this is the MCQs pertaining to FRCR Part 1. It's basically an MCQ revision guide written by Tolan et al. And it's an interesting piece of work because it allows you to just go through, and it's also very, very useful for people studying postgraduate physics nonetheless, and those doing masters in radiation physics or nuclear physics. So let's just pick a few chapters. I'll go through the first chapter today, and the first chapter is Fundamental Properties of Matter, Radiation and Radioactive Decay, which is number 3. So here the foreword is about radiologists relying on the Aunt-Mini pattern recognition approach to interpret the images. It's about how it used to be 30 years ago and what we've done now, the appreciation of the technological advances, and how rapid it has been. And this book is good. It says that once you've digested its contents, it'll provide you with long-term sustenance. The authors are amongst the first students and teachers to experience the revised syllabus and examination for Part 1 of the FRCR in December 2002. So that's about, I think that's 18 years in the past. In a format which is clear and concise, they've covered the radiation physics relevant to imaging, including X-ray radiography, computer CT scanning, radionuclide imaging, also those aspects of radiation protection which are relevant to clinical application, and the legislative aspects pertaining to FRCR qualification, and all the accompanying legal aspects as well. So the volume's invaluable not only to candidates for FRCR Part 1, but as a continuing source of reference for radiologists at a later stage of their training. Basically, they don't want you to throw the book in the bin once you're done with it. They want you to read it and share it with yourself, with your colleagues, peers and students perhaps. So that's the foreword, a bit of a plead. And here's a list of abbreviations. Most of them are quite straightforward. CT scanning, dose area, product, half value layer, ionizing radiation, medical exposure regulations 2000, and kilovolt linear attenuation coefficients. Some of them are nice, like thermoluminescent dose meter, TLD. So that's how things are for now. So the introduction talks about radiology being the most competitive and rapidly expanding specialty in medicine due to its non-invasive diagnostic value, and it's a combination of technological advancement and overarching legislation, and that are preserving the ethical integrity of this field of medicine. So the authors are allowing to provide accurate questions representative in style and content of the new exam, including more difficult topics, and to help students learn essential facts and direct further reading in areas of their particular own specific weakness. And it provides a couple of chapters on legal support as well, the legal framework, which is very nice for students of postgraduate radiation physics. So the layout of the book is good. There's a mock exam in there as well, and every option has its explanation in there as to why is the option true or false. So that's pretty much it. I think we'll dig in. So the first question pertains to electromagnetic radiation, EM waves, or EM spectrum, EMS. We call it EMS or EMW. We call it EMS to save electromagnetic spectrum every single time. We just call it EMS. Concerning electromagnetic unattenuated radiation travels in straight lines, not necessarily. Attenuated radiation travels in straight lines, but they're at an angle to the collimated radiation. The inverse square law applies equally to both extended and point sources of radiation. Yes. The inverse square law applies to all types of high energy and electromagnetic radiation. Not necessarily. It doesn't apply to high energy sound waves. It's composed of. It applies to gravity waves and EM waves, but not to sound wave that are longitudinal, and the S seismic waves, the S-shaped seismic waves. It's composed of particles and waves, and yeah, that's duality. Yes, de Broglie and Huygens principle. It comprises of E and B fields oscillating perpendicular, orthogonal to each other. Yes, orthogonal to each other. And regarding EM radiation, the frequency of electromagnetic radiation is directly proportional to its energy. Yes, that is true. Correct. And the energy of a photon of EM radiation is typically expressed in joules. And yes, all energy is expressed in joules anyway. The speed of a photon increases with the energy of the beam. Is that true? Let's just see. Yes, that is true. And the speed of EM radiation is independent of the medium to which it travels. Well, it is at first when it's traveling in vacuo, it's constant, 300 millimeters per second. But when it goes through gel or phantoms, or different types and kinds of matter or fluids, its velocity does experience a change. And gamma and X-ray photons differ from each other in frequency and wavelength. They differ in terms of this causality and their nature and their expressivity as well. But one of the ways to identify differentiate between photons of gamma rays and X-rays would be their frequency and wavelength. Yes. The following are the examples of EMR. That's not. So this is not. And that's not either, because that's particle emission. So that's EMR visible, but these two aren't. All forms of ionizing radiation are used in diagnostic medical imaging. Nope. Are attenuated exponentially in matter. Yes. Exponential. Look, attenuation is an exponential phenomena to begin with anyway, regardless of matter. They can cause cell damage. Nope. Obey the inverse. Yes. May cause heating. Yes, they do. So regarding the nucleus, the atomic mass number is the number of protons in an atom. Yes, the atomic number defines the element. Well, not really, not completely. The nucleon number, protons plus neutrons, define the element. A nucleus may only exist as it's at only one energy level. Nope, it's not true, because of the stochastic randomized nature of element of particle emission and particle absorption. A nucleus may absorb or emit particles, and it can undergo angular momenta excitation, or a decay rate de-excitation due to these phenomena. And a nucleus may so neutrons and protons are loosely associated within the nucleus. No, they're not. They're tightly held by strong nuclear force. A radionuclide is a nuclide whose atoms are unstable. Not all of them are. Well, they're not unstable. They are decaying. They are unstable in terms of the fact that they may disintegrate. It's undergoing disintegration, and it's not undergoing chemical instability. It's undergoing nuclear instability, which means that the particles are undergoing emission, but they're not denaturing or decomposing. Decay here does not mean decomposing as in the biological sense of the word. Nuclides are components of the nucleus. Nope. Are radioactive? Yes. This, well, may or may not be. Radionuclide is, but a nuclide is not. Of the same element with different atomic number, then those are isotopes. Of the same element with different atomic masses, no, with different nucleon masses, are defined by the atomic mass number only. Nope. Are fully defined by the atomic mass number and atomic number. Yes. The number of protons and neutrons concerning atoms, the number of P and N are equal in a stable. No, it's the number of P and E that have to be equal in a stable atom. In a tungsten atom, transitions from L shells are more likely than from yes, because K shell electrons are closely held by the nucleus due to nuclear charge, weak nuclear force, strong nuclear force, and electromagnetic attraction. Because a nucleus is positively charged, electrons are negatively charged, so they're very difficult to get rid of. Concerning atoms, electron binding energy is the energy required to promote an electron to a highest energy orbital level. Using the helium atom as an example, the K shell contains 4 electrons. No, it contains 2. So it's 2, 8, 8, 18, 28. Positrons and electrons are of equal mass. No. Electrons have mass and positrons have antimass. Antimass is the inverse of mass, but it's negative mass, but it's the same quantity. So regarding electron orbital shells, electrons exist in a continuous spectrum of energy levels around the nucleus. Yes. The binding energy of the K shell is always greater than that of the other shell. Yes. The valence shell is the source of characteristic radiation. That's for particle emissions, not for nucleus. Radiation is coming from the nucleus, not from the shells. But if it does come from the shells, in case of X-ray emission, yes, then obviously it'll be coming from the shells and not the nucleus. But for radionuclides that are undergoing radioactive decay, it's coming from the nucleus and not from the shells, unless they absorb or emit a beta particle thereafter. Atomic number has no influence on the K shell of the bind. Yes, it does have an influence because of nuclear charge, electron affinity, electron binding energy, electronegativity, and the number of shells and the nuclear charge, strong nuclear force, weak nuclear force. It does have some impact. Each shell may only contain a set maximum number. Yes, that is true. That is correct. Concerning electrons traversing in an X-ray tube during the radiographic exposure. So concerning electrons traversing in an X-ray tube during a radiographic exposure, they travel from cathode to anode. They ultimately dissipate most of their kinetic energy as heat. In fact, that's 99% being dissipated. It's far less efficient even than an incandescent bulb. They are deflected by the E fields. Yes, not only that, but they experience deflection, minute deflection from B field as well. But it's compensated, and there are measures to keep them collimated, lineated more so. And the electron volt is a quantity only used to measure electron energy. No, not really. It's for all particles, almost all particles and photons as well, for photoelectric emission and electronic ejection. So they are unaffected by the loss of the vacuum seal in the tube. No, it's all about vacuum because this is happening in an in-vacuum state. Without the vacuum, they'd be all over the place and be very hard to keep them collimated. The next one is there's no change in the atomic number of an element after the following processes. Isomeric transition, yes. Why? Because there's a video I've done on isomers, isotones, isotopes, and isobars, and it would really help for you to understand that most of those don't affect the A number. They affect they don't affect the Z number. They affect the A number. So the K shell capture capacity and tendency, it undergoes a change. Does not go change, and isomeric transition does not go, and then K shell capture does undergo change, and the internal conversion doesn't go under change, and the positron emission obviously goes because it has to come out pairing with an electron for eventual annihilation into a gamma photon. and there's no change in the chemical shift either. So that's a typical one. There's no change. There's a negative there, and you have to check whether the following procedures are affected. And the first one is not affected, the second one is affected, the third one is not affected, the fourth one is affected because of its particulate nature, and the fifth one isn't affected either because of the overall number of electrons staying the same. Radioactive decay may be directly accompanied by the following types of emission. It is for A, B, and C, but not for Bremsstrahlung. For Bremsstrahlung, you have to have certain conditions, and those conditions are expressed as small spikes on the graph. Okay, so all of the isotopes of an element have different nucleonic masses, and they occupy the same position in the periodic table. Otherwise, the periodic table would be very, very large. And they decay by emitting radiation. Nope, not necessarily. Like oxygen 16, oxygen 18, phosphorus 37, phosphorus 32, sulfur 34. They're not always radioactive. With question number 13 is, with radioactive decay, metastable nuclides tend to release gamma radiation to reach a stable ground state. Yes, that happens a lot, often, very often, for me not to remember that. And the alpha emission reduces the number of neutrons in an atom by 2. Yes, it does, because it's 4 and 2, 2, 2. So a gamma emission results in no change in it. Obviously, yes. The atomic number increases with a beta minus. Yes, it does, because beta minus is the opposite of beta, normal beta, regular beta proper emission. A nucleon is another term for a metastable radioactive nucleus. That's not true. A nucleon is another term for a metastable radioactive. Nope, it's not. A nucleon is just a name given to a proton or a neutron, an entity that resides within the confines of the nucleus in an atom. Concerning radioactivity, a radionuclide decays by a factor of about 1,000 in 10 half-lives. Yeah, it does, yes. Yes, it does. I just was verifying that the radionuclide decays by a factor of about 1,000 in 10 half-lives. So I started off with 1,000 grams, and it was 1,000, 500, 250, 125, 62.5, 31.25, 16, 8, 4, 2, 1. So that is a factor of 1,000. So it's reached 1 here after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 10 half-lives, the difference between 1 and 1,000 is a factor of 1,000. So that is correct. A radionuclide with a long half-life poses a lower hazard with few constraints than are necessary for safe storage than one with short half-life. No, that's exactly the opposite. A radionuclide may emit both beta and gamma radiation. Yes, a becquerel is a measure of radioactivity where there is 1 decay per minute. No, that's the lambda per second. Becquerel is A equals minus lambda nuclides. So it's a measure of radio where there is 1 decay per minute. It's 1 decay per second, and it's 1 disintegration, decay per second, not per minute. Minute is not an SI unit. And specific activity is the radioactivity of unit mass of a radionuclide. That is correct. So specific activity, it doesn't have any units, it's a ratio. It's the radioactivity of a unit mass of a radionuclide. The following are true of the radioactive material. A radioactive nucleus must contain an excess of neutrons with relative to protons. Not necessarily. We have plenty of examples of americium and other isotopes that have a very close number of neutrons and protons, but they still manage to be radioactive. It's more down to the nature of the. It is true in some cases, but it can't be generalized. I'm sorry. The following are true of radioactive material. The half-life is the time for half of the radioactive nuclei in a sample to decay. Yeah. The half-life is directly proportional to the decay constant. Is it? Equals minus lambda n, and lambda is log natural 2 over half-life, so it's not proportional to lambda, and lambda is proportional to activity. So if it's inversely proportional to lambda, then it has to be inversely proportional to activity. It can't be. So it cannot be inactivated by extreme cooling. Yes, radioactivity is not a thermal phenomena, although it may be thermonuclear in nature, but thermal effects are a byproduct, but it's not inactivated by freezing or cooling. It's a nuclear event, a stochastic nuclear phenomena, not a temperature triggered or temperature dependent anomaly. The mean lifetime of a nuclide is longer than the half-life. It is, yes, the mean overall. Question number 16. The following statements regarding radionuclides are true. None of them are true, and I'll just have the effective dose from a radiopharmaceutical is only dependent on the volume to be given to them. No, it's also dependent on the concentration, the body weight, dosage per kg, so yeah, it's dependent on the mass, the bone density, age, sex, and previous hereditary predispositions to carcinomas, and that's how the dosage is figured out, calculated or configured. And it's also down to the accuracy of the apparatus executing the dosage of the radiopharmaceutical. And each radionuclide emits only one photon energy. That's just bizarre, too bizarre to just even stop at it. It's not true. Isotopes which emit both beta and gamma are not used for medical purposes, either therapeutically or diagnostically. That's wrong. We have plenty of examples of cobalt, of iodine, of phosphorus, of barium that do. And a gamma-emitting nuclide emits a continuous spectrum of photon energies. No, it's just gamma. It just emits gamma. It doesn't emit microwave or visible, or you wouldn't be able to detect it only through a gamma camera. You shall be, but it doesn't emit anything else. The decay constant of an isotope changes accordingly to in accordance to chemical bonding that may take place with another atom. Nope, it's independent of it. The nucleus of the radionuclide shall continue to decay stochastically at the same rate, regardless of the chemical bonding taking place in the external valence outermost shells of the atoms of the element. Regarding radioactive decay, the activity of radionuclide is its rate of decay. Yes, A equals minus lambda. And that's log natural 2 over effective half-life, which is a reciprocal sum of the physical and the biological half-life. So that's the whole formula. That is correct. The range of a beta particle in water is about 2 cm. Nope. Decay occurs at random. That is correct. It's stochastic. Only beta emission is detected by Geiger-Müller. Nope. They detect alpha as well. The decay constant is a probability of the decay of an atomic nucleus per unit time. Yeah, that's that. Had it said per minute, it would be false, but because it said per unit time, that's correct. So that concludes the first 17 questions, all the 17 questions of the first chapter, which is very basic. So we'll move on to the second chapter soon. Thank you for watching.